You want to see the whole thing, don't you? I knew you'd be back. I knew I couldn't get away with just giving the equation for dipole radiation. I knew you'd want to see it. Well, we'll give it a shot. I predict you'll be begging for mercy before we get to the end. But let's do the E and M, or let's do some of it and see what happens when the light pushes this charge up and down in this particle. And I want to do it because it'll show you a lot of the approximations and how many approximations go into getting something as complicated as the electromagnetic radiation from an oscillating dipole into such a simple little expression. There's no way it should be that simple, right? Well, with enough approximations, it is that simple. But they are very good approximations. So we're going to describe this, this dipole moment as really just oscillating charge up and down. We'll call this Q plus cosine omega t. I'm sorry, Q plus equals the Q plus charge equals some Q cosine omega t. So just an oscillating magnitude of positive charge there. And Q minus equals minus Q cosine omega t. Okay, so it's oscillating in phase, plus minus plus minus. And that's how it behaves. Now let's draw it in a way that's more useful. So we're going to draw it on an axis like this. And we're going to say this is the center, and one of the charges is up here, and it's d over 2 up. And say that's the plus charge, and the minus charge is down here, also d over 2, because we're imagining that it's a particle of diameter d. All right. So that's what those two things are doing. And what we want to do is think about some point out here, some point P, and say, what is E of P? Because if we could calculate the electric field due to this oscillating charges, then maybe we could see if that looks like light. Hopefully it'll look like light. So let's see. You can draw, we want to draw a line from the origin. We're going to call that R. And we're going to draw a line from the top charge. We're going to call that R plus, and a line from the bottom, and we're going to call that R minus. So each one has their own distance to point P. Slightly different. Okay. Let's see. So we want to calculate EP, but what you want to do is start with potential. So it's very complicated to do this completely with fields. You might as well put off the field as long as you can. So at first we'll write the potential, and then we'll take its gradient to get the field. Okay, so we don't really want to get E at point P. We want to get the potential V at point P. Well, we can treat these as point charges very nicely. So we really just call this, it's what we learned, if you took 102x, it's kq over r. Now we don't use k, Coulomb's constant, we use the 1 over 4 pi epsilon naught. That is equivalent to Coulomb's constant, 9 times 10 to the 9 in MKS units. And that's k, and then q is just, for the positive, it's q cosine omega t, and that's over r plus. But it's not really omega t, because we are thinking about the field here due to a change here, and it's not instantaneous. We're talking about light. It takes the time that it takes light to go from here to here for the potential here to be updated due to the instantaneous change in charge here. So it's really not cosine omega t, it's what we call a retarded potential. It's cosine omega t, or cosine omega, and then the time quantity is t minus how long it takes, r plus over c. That's supposed to be an r. So that's called the retarded potential, q cosine omega t minus r plus over c. And it's over r plus because that's how you write a potential. And then that is minus, because we have a negative q here, times the cosine of omega, and also a retarded potential t minus r minus over c. And that's over r minus. All right, and 1 over 4 pi epsilon naught. So that, so far, don't look so bad. That's how you write the potential. And what we're going to do is Now we have to simplify it. You could say we're done, start taking a gradient and get the E field, but you don't want to do that yet because you'll get a mess. The reason you do these sort of long derivations and simplifications is to try to get something that you can use your intuition on. The answer we're working towards gave us the 1 over wavelength to the 4th, so that's why the sky is blue. And the simple directional dependence tells us why the sky is polarized. You wouldn't get that if you just took this big mess and took the derivative to get the E field. So we're going to simplify the 4 parts. And those 4 parts are r plus, really 1 over r plus, 1 over r minus, the q cosine term, the q r plus cosine term, and the q r minus cosine term. We're going to simplify those independently and then stick them all back together. Okay, so let's do r plus first. R plus. How are we going to simplify that? You could say it looks like r plus and r minus are pretty much equal to r. That would be oversimplifying it, because if that were the case, it's a plus and a minus the same distance, then the potentials would cancel and you get 0. And you can see that here. If I make r plus and r minus the same, then we get 0. So you don't want to overdo it. So first, let's look at this and say, okay, another quantity we care about is the polar angle. So p is at some radius, it's some angle theta from the polar axis. And you look at this r plus and apply the law of cosines. Okay, so r plus squared equals this squared plus this squared minus 2, this times the cosine of that. So look it up, law of cosines. So I'm going to take the square root, because I don't want to write r plus squared, I want to write r plus. And it's d over 2 squared plus the other one squared, r squared, minus 2 d over 2 r cosine theta. All right. There's r plus. And now we actually want 1 over r plus. Right? The one part we're looking for here is 1 over r plus. Well, okay, that's d over 2 squared plus r squared minus 2 d, I'm going to write dr cosine theta to the minus 1/2. So all we did is invert it and simplified that. Right? That's all we've done so far. Okay, let's keep going. Let's see. So now we want to simplify this. And let me see. Yes, we're going to expand around d equals 0. So when a physicist says that, they mean we're going to do a Taylor expansion. And we're going to expand for d around d equals 0. So that literally means we have to take this expression. I'll say it approximately equals 2, because we're only going to do 2 terms, and take its derivative with respect to d. The derivative, plug it in, and really do the full Taylor series, right? So the first term in a Taylor series is you don't take the derivative, you have the actual expression. The actual expression evaluated at d equals 0. Well, let's see. Evaluate the actual expression at d equals 0, that's 0, that's 0, that's not 0, that's r squared. And it's r squared, 1 over its square root, it's 1 over r. Right? So the 0th order term in the Taylor expansion is 1 over r. And I could even write, if I really wanted to go all the way, d minus 0 to the 0 power is 1. I'll just leave that out. Okay, the 0th order term is 1 over r. Okay, so now for the next order term, first order term, we take the derivative of this with respect to d. Okay, so what is that? So minus 1/2. All this stuff to the minus 3/2. But in the stuff, we're going to plug 0 in for the d. Okay? So let's go ahead and plug it in the 0 to make sure we get the right thing. We get 0 plus r squared minus 0 to the minus 3/2. Right? And then we would multiply by this stuff, the derivative of what's inside with respect to d, right? That's part of taking the derivative. So you would end up with, what is that? That's d squared over 4, so it would be d over 2. But we're going to plug in 0, so that part would be 0. the derivative of that with respect to d is 0. So there'd be another 0. We could write it, I guess, plus 0. And then minus dr cosine theta, the derivative of that with respect to d is minus r cosine theta, and that part doesn't become 0 when you plug in d equals 0 because it doesn't have a d in it. So you have a minus r cosine theta. Okay, and that's not to the negative 3/2, that's just the derivative part. And then that is times d minus what we're expanding around 0 to the first power. And if we wanted to keep going, we would do the next order term, but we're not going to. We're going to expand just to the linear part. That's all we need. Okay, so let's see what's left when we're done with all that. 1 over r plus is about equal to 1 over r. And let's see what's left, minus 1/2. And this is 1 over r squared. That's 1 over r cubed. All right, 1 over r minus 1/2 went to minus 1 over r. I wrote squared here, but it's got to be cubed. 1/2, 1 over r cubed. And then what's left here is, r cosine theta and times d. So r d cosine theta, and sure enough, of course, that's where my cube and square came from. R d cosine theta, and those combine to give you 1 over r squared. So it's 1 over r squared d cosine theta. And that's everything. Okay, so 1 over r is about equal to, or 1 over r plus is about 1 over r minus 1/2, 1 over r squared d cosine theta. So we can write it nicely then. 1 over r plus equals, we'll just call it equals now. We're going to pull out a 1 over r times 1 minus 1 over 2r d cosine theta. And that's one of the 4 parts that we needed. 1 plus d cosine theta, yeah, over 2r. Similar, an exactly similar derivation would give us 1 over r minus. All right, so everything would be about the same, one little minus sign to be running around, and that's equal to about 1 over r times 1 plus 1 over 2r d cosine theta. And now we have 2 of the 4 parts, right? So this was, I didn't label 1, 2, 3, 4, but we have now 1 over r plus, and we have 1 over r minus. And now we have to deal with the cosines. Okay, so let's keep going and say, oh yes, cosine omega t, omega times the retarded time r. I'm going to do plus or minus first. I'm going to do plus r plus over c. What is that equal to? Well, it's equal to the cosine of omega t and then minus r plus over c. Well, we just solved that. We said r plus is, we got 1 over r plus, so all we got to do is invert it and put a 1 over c and then invert this thing, invert this one. And the 1 over r will invert to just be an r, so it'll be r over c, and then that thing to the negative 1. Yeah, so let's see, so it'll be t minus r over c times this whole big thing, 1 plus d cosine over 2r to the minus 1. And God knows how many parentheses there are to close. There we go. All right, so now we've plugged in our r plus in here, so now we have this down to just r's, that's good, and just thetas, and 2r, right, that's a 2r on the bottom, right. So now we're going to do another expansion. So 1 over x around 0 is 1 over 1 plus x around x equals 0 is 1 minus x. You could do a Taylor thing to prove it to yourself, but that's basically true. 1 over 1 plus x, if this is small, is about 1 minus x. Okay? And this is the place where that's happening. Okay? this is 1 over 1 plus something small. How do we know it's something small? Well, we have all of our approximations. So we are assuming basically that the smallest thing in the system is d, the smallest length scale. That's the size of the scatter, the separation of these charges. That's much smaller than the wavelength, and the wavelength is much smaller than r, how far away the point is. So this is one of those approximations. We have d divided by r, the very smallest thing divided by the very biggest thing, and cosine is just about 1, on the order of 1. So we have 1 over 1 plus something small. So what that lets us say is that this is equal to the cosine of omega t minus, and then r over c still, and instead of 1 over that, we say 1 minus d cosine theta over 2r. Close, 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 like that. All right, let's see. Now we want to go ahead and multiply that out. Let's see, we have r over c there. Some reason I have this as an omega. Oh yeah, let's just distribute this whole thing out, and we're going to get cosine of omega t, right? And that's minus r over c with omega, minus omega r over c, and then, oh, let's see, that's plus, the r's go away, d cosine theta over 2c with an omega in there. So all that together, oh, well, let's just put it all together, and then I'll change it. Omega, the r's go away, over c, and then we have a d cosine theta, and there was a 2 in the bottom, and the r's went away. And the only thing I want to change here is I want to start talking about k. I want to start talking about the wave number k. Because remember, omega, always true. I'll write it here because it's always true. Omega equals ck. That was like our dispersion relation. Omega equals the speed times k. So omega over c is k. So you could call this to be simpler, kr, omega t minus kr. That's what we're used to thinking about waves. But you could also do it here. You could call this kd. So let's call this kd over 2. All right. Okay. So now we have a cosine of something pretty familiar here. That's just the propagating part plus some new part. All right. So we could write that as we could use the sum to product rule. All right. So it would be the cosine of this times the cosine of this minus the sine of this times the sine of that. Yeah, so it would be cosine omega t minus kr times the cosine of k d cosine theta over 2 minus the sine of omega t minus kr times the sine of k d cosine theta over 2. All those terms. Now, let's see. Now we got to think about the cosine with the sine in it and the sine with a sine in it. Okay? Because another thing is small. Okay? What's small this time? We have k times d. K is 2 pi over lambda. We have basically d over lambda in this term right here. D over lambda is small. Okay? So this is small, and this is small. Not the sine, the kd cosine theta over 2. When you have a cosine of something small, it's about 1. And when you have the sine of something small, it's about the something. Okay? So what we're going to do is get rid of this one. This one we're going to say is 1. And this one we're going to say is basically the argument. It's just the kd over 2. And what that's going to let us do is write sort of our final part is that this is, I think I can fit it here. Okay. This is, yes, cosine omega t minus kr, and that's just 1. Right, times 1 minus sine times, and then this sign just becomes KD cosine theta over 2. Right? And this was basically the cosine omega t minus r plus over c term. So this is the cosine omega t minus r plus over c. That's getting sloppy, but nobody's watching at this point anyway. Okay? So that is one of the 4 things we had to calculate. So we've now got 3 of them done. We did 1 over r plus, 1 over r minus, and we've now simplified the cosine with the r plus term in it. And now let's say similar derivation would give us cosine omega t minus r minus over c. Do almost the same thing. The only thing that's going to change is one negative sign, and it is right here. This is going to become a plus. So it's going to be cosine omega t minus kr plus sine omega t minus kr kd cosine theta over 2. So now we've got that one. So we've got all 4, okay? And now we got to combine them. But before we combine them, we're going to have a shortcut. You don't want to combine them without the shortcut. Bad idea, okay? So let me go back to R1 and R2. We're going to give them nicknames. We're going to call 1 over R1, this part, we're going to call it A plus B. Okay, even though it's a minus sign there, 1 over R plus, whoops, I have these backwards. Oh no. Let's see, 1 over R plus was supposed to come out as the plus, and 1 over R minus was supposed to come out as the minus. Let's see if I can fix it so fast that we can live with it. Let's see, it's 1 over 1 minus 1 half, and that's a minus because there's a minus there, and the derivative was minus 1 half to the blah, 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 to the minus. Oh, and there's a minus there. And those 2 minuses make a plus, 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 plus. And if you did it right over here, you would have gotten a minus. Whew. I do not want to do this again, okay? So anyway, there you go. That's A plus B. And then over here, we're going to call this the nickname, A plus B, because we don't want to write all that again. And this one's nickname is A minus B. Okay, 1 over R is fine, but A plus B, A minus B. And then this one we're going to call, and let me double check them, because if I have the sign wrong, that would be bad. C minus D. This little part is C minus D, and this little part is C plus D. Okay. And now that we have their nicknames, we can keep going and plug them in and see if we can get the E field. So we're running out of boards here. So let's keep going. So the way that we've set things up, we had our part 1, part 2, part 3, part 4, and our A and our B and our C and our D. We had 1 over 4 pi epsilon naught. And things we can pull out, we can pull a Q out, right? The cosine term is really all we dealt with. It was Q times cosine, Q times cosine. So we can have a Q here. And the 2 bottom terms, the 1 over R plus and the 1 over R minus, both had R times something, right? I think that's what they had. So we can pull that 1 over R out. I'm sorry, it's 1 over R times something. So we can pull out that 1 over R and then just deal with the A, B's, and the C's and the D's. So if you look at the sequence of terms, it was the cosine with the R plus, and it was 1 over R plus. So that ends up being A plus B times C minus D. So A plus B was the 1 over R plus term, and C minus D was the cosine term. So it's A plus B times C minus D. And then it was minus because the next part was the negative charge. And then it is the I'm sorry, yeah. And then it's the C plus D part is the cosine part, plus D, and then it's the A minus B. The opposite in both cases, 1 over R minus and the cosine with the R minus. Okay, so the reason we did A, B, C, D, blah, 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 is it makes it a lot easier, right? So this becomes AC plus BC minus B, let's see, so AC plus BC minus AD is what I'm trying to say, minus AD minus BD minus AC plus C B minus DA plus DB. Right, that becomes that little thing right there. And a lot of this hopefully is going to cancel. Yes, AC cancels AC, BC, oh, that's not going to cancel, minus AD, and there is minus DA, so minus BD and DB. Thank you. I knew something else canceled, right? And then CB and BC, yeah. So in the end, we get equals 1 over 4 pi epsilon naught Q over R, and two of these combined, you get 2BC minus 2AD. Right? BC, BC minus AD minus AD. There it is. That's the reason we did the ABCD, is that's a lot easier than actually dealing with all of those terms. So now we're going to pull out the 2 and say this is 2Q over 4 pi epsilon naught R, and go with B times C. So now we just need to go back and remember what B and C were. Let's see, B was from the whole A plus B, A minus B, from the 1 over R plus 1 over R minus. It was D cosine theta over 2R. Yes, D cosine theta. And then the 2 we pulled out. C was from the cosine terms that we put together. And, I'm getting out of order. C was from the cosine terms. And yeah, that was the cosine omega t minus kr part, right? Of course, cosine omega t minus kr. Right, okay, so there's BC minus, and then AD, A was KD cosine theta over 2. So we just had a K here rather than an R. K D cosine theta over 2. And let's see, that was supposed to be A, so I'll just double check because, you know, I don't want to mess up. A, let's see, I'm sorry. And then D, what was D? D, yes, I'm sorry, A is 1. So we had 1 minus this thing, so A is just 1. All this big mess left over is D. And D, yes, was KD over 2 cosine theta, and then sine omega t minus kr. So did ABCD save us time? It probably did, believe it or not, okay? So there is a version of VP, okay? But we're not quite through with it yet. Let's see what we can pull out of VP. Let's pull everything out we can. We could pull out a D, a cosine theta, and a 2. I think that's all we're going to pull out. D cosine theta and a 2. Yeah, I was going to cancel that too. Okay, yeah. So Q, D, cosine theta, and it canceled that too, so it's still 4 pi epsilon naught R is going to come out. And what's that going to leave us? D cosine theta over 2, 1 over R cosine omega t minus kr. Right, and then this is going to leave us, what do we pull out of D cosine theta over 2, minus k sine omega t minus kr. and like that. So there's VP. How are we doing? That's VP. Well, now it's time to ditch one of these terms. Which one are we going to ditch? This is 1 over r, and this is essentially a 1 over lambda. And which one is bigger? R. R is the biggest number. Everything's big. 1 over r is big, so 1 over something big is small compared to 1 over something not so big. Okay, so that cosine part we take to 0. If we take that to 0, we're left with VP finally. The potential at point P is minus Q d cosine theta over 4 pi epsilon naught r times k sine omega t minus kr. All right, and the k could have gone in the top, I suppose. Everything's there. The wavelength, the separation, the charge, the position we're at, the frequency. It's all in there. It's good that everything's in there. Right? If something didn't end up in that, that could signal trouble. Okay, so we have our potential. Now, and let me write it down here so I'll be able to see it. Vp equals minus q d k cosine theta over 4 pi epsilon naught r sine omega t minus kr. Okay, just in case I want to peek up at it, I'll write it down there. Okay, we have our potential, and now we want to get the field. Okay, so the E field at P, if you have the potential, is minus the gradient of the potential. So a little bit of E and M there. So hopefully you've heard of the gradient. In spherical coordinates, the way you write the gradient is it's dV dr, and we have the negative from that negative, dV dr in the r hat direction. And then a minus again from over there, 1 over r dV d theta in the theta hat direction. Okay, so this is what we have to do to that to get the E field. Derivatives with respect to r and theta. Okay, well, let's just do that then. It's going to be equal to minus dV dr. So where all does r show up? Oh, it shows up twice. How wonderful. Okay, for the r derivative, let's pull out all the constants. Let's see, minus and the minus in the potential together makes a positive. Q, d, k, cosine theta. And in the bottom, 4 pi epsilon naught. 4 pi epsilon naught. Right? That's everything that doesn't have an r in it. Those are the constants. And then I'm going to put the derivative dV dr in here. So it's 1 over r, and it's sine omega t minus kr. So we'll do the 1 over r derivative first. That's minus 1 over r squared, and we'll just write sine omega t minus kr, doing the product derivative here. And then we will say plus 1 over r, and the sine becomes a cosine, and we have to multiply by the derivative of kr, which is minus k cosine omega t minus kr. I believe that is the derivative. Yeah, that's correct. And now let's see, we got to do the theta derivative. Let's see, so minus 1 over r and dV d theta. Where does theta show up? Oh, just as a cosine. And let's see, it's minus, that'll make that a plus. And the derivative of cosine is, oh, it's negative sine, so that'll bring it back to a minus. And we just have to turn cosine into sine at that point. Q d k sine theta over 4 pi epsilon naught r sine omega t minus kr theta hat. Okay, is that the E field? Yeah, maybe, could be. Let's look at these two terms. We have one going as 1 over r squared, that's the biggest number, and one going as k over r. So this is 1 over r times r, this is 1 over r times lambda. Well, this is the big number, right? R times lambda is big and small, and this is big and big, so this one we ignore. That's small compared to that. Whenever you have two things added, you can always ditch one compared to the other. Okay, so that got us down to just that term. And now let's look at this term and this term. And again, this term goes as 1 over r. That's the biggest number, right? So, and this term goes as 1 over r squared. So we can make this whole term go away. It's small compared to that. This is the biggest of the 3 terms. The other go as 1 over r squared. So we can say what's left, if anything's left, is the E field equals what? We have a kr here. Oh, this minus sign probably hung around. Who cares at this point? Q d k squared cosine theta over 4 pi epsilon naught r, just 1 r, that's why this term survived, times the cosine, the oscillating part, r hat. Okay, so we could think about this E field. We could feel pretty good about ourselves. It kind of looks right. If we were to say, what kind of a scattering amplitude would this field have? We'd say, well, what's pointing vector? Pointing vector is S is 1/2 epsilon naught C, the E value squared. If we just thought about roughly what's the magnitude of the pointing vector, would be 1/2, I believe it's epsilon naught C, E naught squared, something like that. And we'd say, okay, well, what's E naught here? It's just this part, right? The cosine is the oscillating part. And you'd say, we've got to square all this, so that 4 squared is going to become a 16, and times 2 is 32. Hey, there was a 32 in our formula. That's promising. Here's k squared, and then we have to square this. So it's going to become k to the 4th. And that's 1 over lambda to the 4th. That was also in our thing. We're going to have to square this. R becomes r squared. That was also in our thing, right? The energy has to go down as the radius squared to conserve energy. So it's looking pretty positive. The dipole, essentially, QD is squared, and that's QD squared. It would actually look pretty good, except for 2 things are wrong. 2 things are horribly wrong. Cosine squared theta. The whole polarization dependence was based on sine squared theta. How did we get a cosine? It's wrong. Should we have kept this term? No. Where did that cosine come from? I'm not going to track it down because something's wrong. Also, r hat. If we think back to our original scattering geometry, we had 2 little charges moving up and down, and we moved out here to some point P. R hat is that way. If the plane wave is moving away, is the E field going to point in r hat? No. No. This isn't right. We've only done a little part of the problem. We've only done, well, not a little part. We've done a substantial part of the problem. But the problem occurred, we erred here. Okay? This is true. This is how you get the field from the potential in electrostatics. But we're not doing electrostatics. We have oscillating charge. Up and down, up and down. We have currents. Things are changing. We have to do electrodynamics. In electrodynamics, the E field is minus the gradient of the potential. That's part of the story, but it's also minus the time derivative of the vector potential. There's another potential in electrodynamics, and it's not a scalar, so it's not as fun to work with, and it's hard to calculate. Right? In this case, we would have to do an integral of the current flow due to the moving charge to get A, and then we'd take its time derivative, and we'd get a bunch of stuff. And what we would get would look a little like this. I'm probably going to get some sign wrong or something. It'd be kind of like dA dt. Because just because we add something isn't going to help us, right? We have a component here in the r hat direction. It's very bad. Right? So how could we possibly fix that? Well, dA dt will end up being something like, it has mu naught q d c squared k squared, I don't know, 4 pi r. It's in mu naught instead of epsilon naught, blah, blah, blah. Cosine omega t. That's not the part I want to get to. I want to get to this. Cosine theta r hat minus sine theta theta hat, or plus or minus, minus sine theta theta hat. Okay? So if we did this many boards for the vector potential, we could get that too. And it's similar steps, similar approximations. You get the idea. We're not going to do it. But you can see the magic that happens. Okay? So this is minus, but it's minus the dAdt, so I think it comes out plus there. But you can see what happens is here, all these prefactors end up being the same, and it cancels the r hat in the del gradient of v part. Okay? So this actually cancels this. So all this work was for the part that cancels. Okay? And this is the part we need. And once you have that, everything is solved. All this amplitude is right. You get sine squared theta. That's good. That means it doesn't scatter along the polar angle. It scatters forward and backwards into the side, just like we talked about before. And theta hat. Theta hat is what you want. In this coordinate system, you're out here. Here's your two charges. Your some point P out here. You're trying to make a plane. You're trying to make a spherical wave that looks like a plane wave when you get far away. The E field should be in the theta direction. Right? This is theta. Theta hat is that way. That's the proper direction for the E field, not r hat. So I showed you that. I want you to give us some idea of what it takes just to calculate the radiation of a dipole. That's probably the simplest little radiation problem you could do, and it just gets complicated really fast. So even with all those approximations, the approximations allow you to actually calculate a small expression that does describe all the physics you see, the wavelength dependence and the polarization.